I'm super happy to talk about mechanistic interpretability in context learning. I'm at Google, and this has been work with colleagues at Google and ETH Zurich. The motivation is that we wanted to understand the transformer architecture a bit better, and especially its kind of fascinating few-shot learning capabilities that seem to be magically appearing if you just train these models autoregressively. So you can provide like a text description of new tasks, and the model seems to learn based on examples that you give here. And so what we want to study is what happens here. Why does this happen? Just to jump directly to the hypothesis, we think that next token prediction is actually a gradient-based meso-optimizer that is implemented in the transformer architecture. And because there is this nice optimizer in the architecture, you can actually repurpose this for super cool things, for example, in context learning or potentially chain of thought, other things. Just a visualization of the hypothesis. So this huge thing is a transformer, and in the beginning you get the sequence. And the first thing that the transformer is doing is kind of looking at the sequence and deciding what it can consider an input and a target for a data set. So that's what we call a mesa data set. The most simple instance of this is just to consider like a sliding window. So you just slide over your sequence and you consider every element as an input and a target. And then the hypothesis is that the transformer inside the architecture is optimizing, let's say, fast weights, so implicitly parameters that it's learning based on the sequence and using as next token prediction. So first step, copy stuff together, and then learn implicit fast weights. We don't really study this in language models, but only on a very, very toyish setting. So we consider linear dynamical systems where W, the teacher, W star here is an orthogonal matrix. So every sequence is comes from this from a newly, freshly sampled orthogonal teacher. You sample some x0s and perturb a little bit with noise, and you provide this data to the transformer. You train this autoregressively every token, so a next token prediction. So this is not a classification task, so also slightly different as in LLMs. So what is nice about the setting is that we actually know ground truth, a solution to this. So this is recursive least squares. So this is just a least square solver here, regularized for every time step t. You want a new one because you get new data and data per time. So the transformer, to solve this problem very well, needs to implement recursive least squares algorithm, and this actually requires T matrix inversions in the forward pass. And so what can we say about the transformer architecture? Actually, it can solve that problem pretty well. One nice result that was actually in a previous paper is that a linear self-attention layer, so that's a considerate difference to softmax, but still kind of close to the classic transformer architecture, can very easily implement a gradient step. And now in kind of follow-up works, what you can also show, so you see kind of the similarities of the expressions here, that a single linear self-attention layer can actually implement a summand of this, of a truncated Neumann series, so actually can invert these matrices like projected matrices where you right multiply with your xt. Also super well. So this implies that a transformer architecture can actually invert these T matrices very efficiently in log 1 over epsilon when epsilon is the error that you want to have on the final matrix inversion. Okay, so just coming to the last slide. Yeah. So for a single linear self-attention layer, you can study this very thoroughly. When you go deeper, we fall back to linear probes. And yeah, you get, though this is a cherry-picked result, you get here very nice probes. So in the B figure, you see that if you probe for the target, so this is showing so what the transformer should predict at the end. You see these nice over the layers. It's getting better and better and better over time, and you actually can probe for the red as well. So you can probe for the approximated projected matrix inverse here, and you also see this nicely decreasing. So it actually implements this or seems to be implementing something similar in this. And kind of closing the circle, you can now use this as an in-context learner as well.